Welcome to our first recorded lesson for physics. We're going to start with Unit 7. You should have completed the unit overview already with some vocab words and a couple of conceptual questions. We're going to start with simple harmonic motion, and then we're going to move into vibrations, oscillating motion, waves, and sound throughout this unit. Today we're going to talk about periodic motion, simple harmonic motion, period of a pendulum, and Hooke's law, which deals with springs and the elastic potential energy within a spring. A little teacher humor over here, little hee hee ha ha moment since I can't actually see you and joke around in the classroom. You are all missed very much. And you can actually go outside and have a little bit of recess throughout your day with online learning. All right, so periodic motion. It is movement that represents a regular cycle or some sort of cyclical motion, also known as vibrational motion. The vibrational motion can be most commonly thought about with guitar strings. So here is a pretty cool picture of the strings on a guitar vibrating. Some of you might have even pulled a string, pulled it nice and tight, and then someone can kind of pluck that string. You might have done something like that similar. You can do that with a rubber band or anything like that. A clock pendulum is another common example here. We have Cogsworth visiting us from Beauty and the Beast, making a guest appearance. And then over here, we can talk about springs, oscillating motion, and then the elasticity of a spring and how that elastic potential energy gets transferred, and then obviously shows us some sort of periodic motion. As we move forward, anytime you have a force within your periodic motion that is wanting to bring your object that is already in vibration back to its equilibrium position, now we have simple harmonic motion. If you look in the first diagram on the left, we have an object here. This would be the equilibrium position. So that position is obviously if the object is hanging straight down. This object, they're calling it a bob. It could just be any sort of mass that's attached to a string. That string then obviously provides an amount of tension, and this would be called the length or the arm, if you will, of that string. So anytime you move from left to right, that is going to cause our vibrational motion or our simple harmonic motion. The displacement traveled either left or right represents the amplitude, which is defined down here. And then the period or the time that it takes to complete one whole cycle of motion is represented by the variable capital T, and then it obviously is a unit of time. In diagram number 2, we can look over here at this equilibrium position. We have force of gravity acting down on our object, and then the force of the tension in the rope or the string of our pendulum. Those are equal and opposite. So in equal and opposite, we have a net force that is 0, so we'd have acceleration is 0. As we move left or right, we have some sort of swinging motion, and during that swinging motion, the maximum velocity would be at the equilibrium point. The velocity then decreases as it travels left or right up to a position where the velocity eventually becomes 0. At those positions, we still have the force of tension in the string, still the force of gravity acting straight down, and then that net force acting towards the center. This is an additional same diagram, just a further explanation of the net forces. That net force here, if you were to actually calculate, like we did back first semester, the net force between this force here moving in this direction, this force here moving here, in the downward direction, we would then get this net force that is acting towards that equilibrium position. And notice, with simple harmonic motion, there's always going to be a force that is opposing the displacement of that object from its equilibrium position. We can also talk about the period of a pendulum, which is the amount of time it takes to complete one cycle of motion. This is our handy-dandy formula for the period. Notice there's only a couple of different variables in this formula. So this formula has a constant of pi, which we'll go ahead and use, 3.14. This L, okay, is the length of our pendulum. And then G is our handy-dandy acceleration due to gravity value. Now, we all know that G acts straight down and should be a negative value. For this particular part of this unit, we're going to go ahead and use a constant positive 9.81. Just for the sake of not confusing us with direction and displacement, we're going to go ahead and just use a constant value of positive 9.81. But the big idea here is that the only thing affecting this period is the length of the pendulum and the acceleration. A lot of you are going to want to think that as soon as you put a massive object or an object with a large mass versus an object with a small mass, that it's going to change the period of the pendulum. But that's not the case. It's only the length of the pendulum and the acceleration due to gravity, which we know is constant. So let's go ahead and give it a whirl. All right, so here's our formula. We've got our formula referenced up here in the corner. We're going to go ahead and work through. Number one, a pendulum with a hanging weight of 500 grams and a length of 2 meters. What is the period of this pendulum? Well, we know our period would be 2 times our value for pi, 3.14, all multiplied. I'm sorry, I put an equal sign right there. We're going to then multiply that by the square root of the length of our pendulum, which is 2 meters, all over our 9.81 meters per second squared. Notice we didn't even use this 500 grams because, like I just said, the mass has nothing to do with the period. Once you go ahead and type that into your calculator, be sure to do the division underneath the radical before you do the square root. And once you substitute those values, you get 2.84, and that value is in 3 significant digits, and that 2.84 is a unit of time, so our unit will be seconds. Moving down here to number 2, we now have a pendulum with a period of 1.3 seconds, and we're trying to find the length of that pendulum. I'm going to go ahead and extend my page here. This time, they give us the period, and we're going to go ahead and we're going to solve for the length. I'm going to go ahead and use a cursive L so it doesn't look like a 1. So this time, all of our other values are constants here, and we're solving for this value. In order to get rid of this radical, that radical needs to be by itself. But before I can do that, I need to go ahead and move the 2 and the 3.14, or that operation of 2 times 3.14, over to the other side. And to undo operation of multiplication, we must divide. So this is going to be 1.3 seconds all over this quantity of 2 times 3.14. Some of you will go ahead and write that as 6.28. That's fine. Is equal to the length of our pendulum divided by 9.81 meters per second squared, and then we're going to take the radical of that. I apologize if this stylus writing is not as neat as usual. It is a little bit hard to get used to. Our next step, in order to go ahead and continue to solve, I need to undo this radical. To undo the radical, I'm going to go ahead and square both sides. So then I'm going to be left with the length of our pendulum, all over 9.81 meters per second squared, is equal to this whole quantity over here squared. I'm going to go ahead and still leave it as it was before so you guys can see every single step that we're following. We're going to go ahead and take this up over here for the sake of our order and organization on our page. Our last step then is to solve for the length of this pendulum. The length is being divided by this 9.81, or divided by this acceleration to gravity, so I'm going to go ahead and multiply. So the length is going to be equal to 9.81 meters per second squared times this whole squared quantity. So 1.3 seconds all over 2 times 3.14, that whole value squared. Go ahead and slide those values into your calculator and put your answer in 3 significant digits. You should get 0.420. That would be your answer in 3 significant digits. And we're going to use meters here because that would be our value there. Moving forward, we're going to go ahead and talk about a mass and a spring system. So obviously these 3 bullets, A, B, and C, correspond to these 3 different scenarios, A, B, and C over here. We can attach a mass to a spring and we can still have something similar to not necessarily a pendulum moving back and forth, but this spring could oscillate back and forth based off of its elasticity and obviously the energy that is being transferred as that object moves. So when the spring is stretched to the right, like it is in diagram A, or part A of the diagram, that spring force is then acting in the opposite direction. So as we displace our object to the right, that spring force is acting to the left. Therefore, we're going to end up with equal and opposite if that object is at rest, or that force is going to move back and forth. We could lose some of that force to friction, depending on the surface, and depending on how your spring is located. For scenario B, we have an equilibrium point. So when that object is here at this equilibrium point, that means that that spring is not stretched at all. It's not compressed, it's not stretched, so the spring force would be 0. For position C, or I'm sorry, part C of the diagram, when the spring is compressed, now our displacement is negative, and we've now changed our direction of our spring force to be in the positive direction. Regardless, the big idea here is that the force of the spring is always in the opposite direction of the displaced object. If we keep going, this is where we run into Hooke's law. This was that big important law that I told you about at the very beginning of the overview, and here is our equation for that. It's very important that you look here. This spring constant is what the K value represents, or the variable K represents, and then X represents our displacement from the equilibrium position. Notice this negative sign is showing that the spring force is always opposite the direction of the mass's displacement from equilibrium, which we just talked about. That force will move the mass back to its equilibrium position, which is what we already discussed would happen in simple harmonic motion. If we go forward, let's go ahead and try an example. So if you look up here, we're going to reference this formula. We know this time we have a mass 2.1 kilograms. It's attached to a vertical spring. Notice our spring is moving up and down now. Our spring is stretched from its equilibrium position 6.2 centimeters from its original position. And we're trying to find the spring constant. So K is going to be what we're solving for. We know in this case our force, because our spring is vertical, is actually force due to gravity, which will be mass times acceleration due to gravity. We know our mass is equal to 2.1 kilograms. We already know G is a constant. We're going to go ahead and stay with that positive value just for the sake of the negatives and how the negatives are going to work out in this equation. And this time we know our displacement, X, is 6.2 centimeters. Notice it's down away from the equilibrium position, so they're going to go ahead and use a negative 6.2 centimeter value. Now we're going to go ahead and just convert that to meters and use that value. So as we go ahead and substitute, let's take these values and plug them in. So our force is going to be force due to gravity, so we'll have 2.1 kilograms times 9.81 meters per second squared. That represents our force. And on the other side of our equation, we're going to set it equal to a negative spring constant, which is what we're going to solve for, times our negative displacement, 0.062 meters. Notice over here on the right, we have a negative and a negative, which is going to make us have a positive value. So that's why we're keeping our acceleration due to gravity positive here, just to work out these negatives, or these opposite directions, if you will. So in order to keep our constant by itself, K, on the right side of our equation, we're going to go ahead and we're going to solve for K by dividing by this. These negatives are going to become positive, so we're going to go ahead and divide by 0.062 meters on both sides. And once we do that, we're going to go ahead and get a spring constant value. We're going to end up taking this 2.1 kilograms times 9.81 meters per second squared, all over 0.062 meters. Now notice up here at the top, we've got a kilogram times a meters per second squared. So kilograms times meters per second squared, or a unit of force, is actually a Newton, and we're going to divide by a meter. So when we go ahead and put those values into our calculator, all right, you should be ending up with a value that has a unit of Newton meters. my apologies. You should end up with a value that has a unit of Newton per meters. So if you plug those into your calculator correct in 3 significant digits, you should get 332 Newton per meter. And that's going to be our spring constant value. Pay close attention to this unit here. You're going to get some problems later in your homework that give you values with this Newton per meter formula, or I'm sorry, Newton per meter unit. I know that that's not necessarily something familiar from a previous formula, but just understand that that represents the K value. Okay, last but not least, our little chat about elastic potential energy. We've been talking all year about this law of conservation of energy and how energy is conserved or transferred from one form to another. It is the same thing here. We can talk about our strings, or in this case, we can talk about a bow and arrow. So if you pull a string, if you stretch it, if you compress it, if you pull back that bow and arrow and stretch and compress there, that elastic potential energy is the type of energy that your compression or stretched spring then has. Once you release that, in this case, our arrow's energy would become kinetic as it travels towards its target, and therefore the elastic potential energy would be transferred into kinetic. Or in a spring, it could be transferred to kinetic energy of your object, which could then be transferred to friction or other forms of energy that would then bring your object back to its equilibrium position. As we move forward, make sure that you are referencing these notes. They'll be posted on Portal, and they'll also be posted in Teams. This is your homework for the evening, 1 through 7. If you read the instructions up there, it says copy and solve each problem. You can do them right in your notebook. You can need to show all work. Please box your final answer. Leave your answer in 3 significant digits, units, directions, and for any conceptual answers, use complete sentences. If you will, please, please, please make sure you have your scanner apps downloaded so that I can grade your work. This will be the first homework assignment that you have, and have a great time. Stay productive.